All right, welcome back to our slides on OOP and ADTs. Lots of acronyms today. And let's get right on into it. Let's scroll down. We were talking about how to implement a vector from scratch. So we know what commands a vector needs. That's the ADT part. That's the abstract data type. How does a vector respond? What does that look like? It's like a little black box from our perspective as we're thinking of it as an ADT, but we also want to know how to implement the thing. So we have decided to implement a vector using three member variables: capacity, num items, and the array, which is secretly a heap array. And we know how to do all of these operations. Go to a place, it's really just go to a place of the secret heap array that we're not showing the user, telling them about. Dot size, that's return num items. And then pushback is the fancy one that maybe needs to resize and copy things over. But yeah, there's two cases to that. So I want to remind you of that, and we'll have an example about it. But I also have a fun like meme picture that I found, or I think a student sent me on the internet once upon a time. So this is ADT versus like data structure all over again. So from the perspective of somebody who's like the user, they're using this ADT, they're using the vector. They see the turtle from the outside. Like think of the turtle as like an abstract data type. It's like you've got all these things, I know what they do, but I don't know how they're implemented. Whereas if you are the implementer of the ADT, of that library, you know about the data structures, and this is what a turtle really is made of, for example. And so it's just a funny example of that. So you can kind of see the difference again, right? So the ADT is just like, what are the commands that I can use and how does it respond? Like, what's the black box that I'm able to, and like the list of operations I'm allowed to do, and the types kind of they give back. And then the data structure idea is like, what does it really look like in memory? What's really going on under the hood? Okay, so that's a funny example of that. I hope it's coming back. And with that, let's have a little example about pushback. So let's remember, because again, the name of the game for most of this class is I'm going to draw pretty pictures, the prettiest I can draw, of things that you go off and implement. Okay, so there's not going to be a lot of me giving you code. There's going to be me giving you pictures and you turn it into code. That's a new thing for CSCI 41. Okay, so that's what I got to get you good at. So let's talk about pushback. So let's say that memory looks like this. Stack is this. Heap is this. Stack is all these things, by the way. So we're in pushback. We're in the call to pushback. And so we have the 3 is like the number we want to push back. That's the parameter. We also have the current vector we're working on. We're trying to push back to V. So we also have all of its member variables available to us in the body of the pushback method. And then here's what the heap array looks like. Okay. Num items is 2, capacity is 4. So if I run this line, v.pushback3, what changes? Can you draw or just like imagine drawing over this slide and see what happens? What should happen? Can you describe it? So here, so if it's 3, remember what it's going to do. It's going to, so what's the next valid index? It's this one. How do I know that? It's num items, right? If there's 2 things in my heap array, then the next open index is the num items index. That's pretty nice because the size is like, it's always up to index 0 to size minus 1, and this is size, so size is size minus 1 plus 1, which is the next open index. So that's where the 3 is going to go. It's going to go to index num items, and then we'll advance num items. But we could have only have done that, right? We can only do that when num items is less than capacity. We have to check, all right? It's got to be less than. If they're equal, then we must resize, okay? But that's the idea for case 1. I hope that's making some sense. The devil is, of course, in the details and the implementation, but I hope you can kind of see how it's happening, at least on paper. All right. And now this is case 2. So here, again, try to pause the video. We want to do this. We want to run this. v.pushback5, where 5 is the value we're trying to push back. That was the parameter. And then we've got this vector. So we have access to its member variables and its heap array. So what needs to happen? Can you draw it? Can you at least think about it? All right, assuming you gave it a good try, let's talk. So what needs to happen? Num items is equal to capacity. Num items is not less than capacity, because that would allow for case 1. But oh no, we're in case 2. What do we got to do? We need to resize. All right, so we have to resize. So we better make a new heap array of at least 1 bigger. And the standard way of doing this is we're going to make a double size heap array. So our capacity is 4 right now. We're going to make a size 8 array on the heap. That allows for the most efficient pushback implementation. All right. So yeah, that gives us a size 8 heap array, and like we've got that in a temporary variable, like I don't know, new array, something like that. I don't know. It's pointing to this, and it's really pointing to the first element. Maybe I should be more precise, because this will help with your implementation. Sorry, that arrow is going to be in the way no matter what. So like that, yeah, I've got this new array. I can make it on the heap. It's a local variable for us, all right? And then what you want to do is you want to copy over everybody from here, right? You want to copy the 1, 2, 3, 4 into this new one, and then you're good to get rid of this array. Yeah, you can get rid of the old array and say delete R if it's still in there, that's fine. Get rid of the thing. So now it's gone off the heap, and then you say, okay, my R is now this new one. Okay, so you're going to chop off that pointer, and where's a good place? It's just like get rid of that pointer, and you say that R is now this one. It's whatever new R was. So you're going to do that. Sorry for all the arrows everywhere, but I hope you can see what's happening. So that's happening, and then you're good because you'll also double capacity because that's really what's happened. And then you're good to do case 1 stuff, right? So you can add the 5 to the next open index because num items is now assuredly less than capacity. 4 is less than 8, so you can put it in index num items, which is that open index, which is index 4. 5 goes there, increment num items, and we did it. Isn't that fun? So like that's more stuff to do, of course, and the order really matters because you don't want to like delete the old array before you've copied things over into the new one. You also have to remember to change where array is pointing. That all needs to happen. But as long as you do that in that kind of order, then you're set. So I hope that's coming back to you. At least on paper, you can understand what needs to happen because that's going to inform the way that you implement it. All right, and that's coming up. That's going to be our next lab. So yeah, let's go back to these ideas. So we know about all of the algorithms, kind of at least at a high level. I haven't shown you code, but you can think about the code. Can you imagine like how fast these methods are on our custom vector class? How fast is it to do all of these things? If you think about it, size, right? That's just like return num items. It's really fast. It's look up whatever our member variable was because that's where the size is sitting. So that's like one line, right? That's nothing. So that's very fast. There's one line of code. No matter how many things are in our vector, it's just like, give me back the value of whatever that int held, which is going to be called constant time, right? We call that constant time. It's just one line of code, and that doesn't change regardless of how many elements are in the vector, which is also nice. And then .add is similar. .add is, well, you want to go to index 2? Sure. I guess there's only index 0 in this example, but you get the idea. You want to go to index 0? Well, I'll just go to that heap array and go to that same index. So that's just like calculating an offset in memory and dereferencing it secretly. We've learned about that now. And that's not too hard either, right? It's again a line of code. It goes somewhere in memory. So it's like calculate offset and dereference is like 2 steps of real execution inside of your processor maybe. But again, regardless of how many elements are in your vector, in your heap array, it's just an offset. You can calculate the address and immediately go there. It's a random access thing, right? So again, it's constant time. Even if you had 1,000,000 elements, you can very easily and quickly get to the 1,000,000th element or the element halfway through. It's just an index. Okay, so that's .add. It's again very fast, constant. And then pushback is the weird one. Right? We have 2 cases for pushback. One is conceptually much easier than the other. So let's kind of see what has to happen. Okay, so in case 1, what do? We have to go to R of num items, put the value there, and then increment num items. We also have to do like an if statement to make sure num items is less than capacity at the start, something like that. So it's like 3 lines of code, right? 3 lines of code, maybe a condition or 2. And that does not depend on how many things are in the vector so far. There was room, we put it where it needed to go. That's constant time again, right? Constant, it doesn't change. It's immediate, it's quick. And then case 2 is the harder one, right? Case 2, how much time it takes depends on the size of the old array, right? Because that needs to be copied over. Each element needs to be copied over. So if it's a size 4 array, you got to copy over 4 things. But if it's a size like 104 array, then you have to copy over 104 things. That's a lot more. So it depends, right? So it depends on the size of the old array, because everything needs to be copied over as we double the size. All right, so a large array for case 2 means it's going to take more time than a smaller one. So you're still going to do case 1 after you're finished, so it's still +3 to whatever you've done, but it's like n plus 3, where you had n elements in your array so far that you copied over, because you got to copy over all n of those into the new one. Yeah, plus make a new heap array, so it's like maybe n plus 1 plus 3 or something, if you want to be very fancy. We'll count this properly soon, don't worry about it. But do you see how case 2, the amount of time it's going to take is proportional to the size of the old array, which we'll call n, all right? And because of that, it's like y equals n, so it's like the graph of a line. We call that linear time, okay? So I hope you can kind of understand some of that. We're going to learn this kind of analysis in depth real quick, so don't worry about this too much if this doesn't make full sense yet, but this is where we're going. So if you understood any of that, pat yourself on the back. And a very fun thing that I'll kind of explain later, but you'll really get a good feel for it in an upper division algorithms class. If you go into computer science and you transfer, and at a 4-year college, they'll teach this to you and you'll understand it. But crazy enough, no matter what, as long as you double the size of your vector each time, double the size of that heap array when you've run out of space on a pushback, even though sometimes it takes linear time and then sometimes it takes constant time, on average, pushback on a vector in the way that we're asking ourselves to implement it is still constant time. Isn't that really cool? It averages away because of the doubling, because as you double it more, you hit case 1 more often. And so you don't have to pay the price of case 2 too much. And that's why we double. If that makes a little bit of sense, that's kind of the idea. All right, but you can make that precise in an algorithms class. That's very fun. All right, so that's time complexity, first of all. All right, that's called running time complexity. How much work do we have to do to get this job done? The other kind of complexity that we care a lot about in this class is space complexity. What in the world do we need our computer? How much RAM do we need in our computer to run this code? How much memory are we using? All right, when we run our code. So let's think of it in terms of that. So you want the size of your vector. Assume that you already used you already have the vector like in memory. That's already stored. That's not anything extra to you. All right. So like dot size, you've been called on some vector that's already been made in memory. How much extra space does it need for dot size to run? All right, that's kind of what space complexity analysis is. You've already got the vector, but I want to run dot size. How much extra memory does dot size need to run and give its answer back? All right, so it doesn't take anything. It's just not a void method. It's a method that gives an int back, but it takes nothing. So there's no arguments to store, so it doesn't need any extra parameters, but it returns an int. So it's got to kind of save that int away as it's giving it to somebody as it returns. And so if you think about it, you're returning num items, and that's kind of getting copied into somebody else's memory later. So you're just storing, or you're using a space of 1 int. Using 1 int of space, which is 4 bytes of space, just to give that answer back to somebody and copy your int into their int. Okay, so you need 4 extra bytes. And that is constant space. No matter if the size was 1,000,000 or 1,000,000,000, you can fit both of those numbers in a single int, which is 4 bytes. That's great. So dot size was constant space. Dot at, what about that one? So it took a parameter, like what index did you want to go to? It also returns an int, so it's got to use like 2 ints of space. Does that make sense? It's got to use 2 ints of space to get its job done. The vector has already been accounted for. It's just what extra stuff do we need to complete dot at? So that's again constant, right? 2 ints worth of space, that's fine. And that's still not bad, right? Constant space is pretty much as good as you can do. It doesn't matter the original size of the vector. It's still constant. So there's that one. And then pushback, of course, is the harder one to analyze. So in case 1, you can imagine that it's going to be constant space again, because you've already got the space in that vector made, right? You've already got space on that heap array. It's nothing else. You're just modifying an address. It's already got space made for it. But you do have to like store the int that you were given, for example. Oops, I was on this one. You have to store the int that you were given because pushback takes something. So like there's also plus an int, but the bulk and the bottleneck is in case 2, right? for when you have to allocate a new array of size. Say, pretend that your old array was size n, capital N is what we use a lot in analyses. You have to allocate size 2n, right? You're adding 2n worth of space onto the heap. And for a split second, both of these arrays need to exist, because you are going to eventually get rid of the old one and like reclaim that memory. But for a split second, while you copy it over, both of them have to exist at once, right? So you're adding 2n of space. Oops, I keep going to the wrong slide. You're adding 2n of space, and then you have to like store a few extra ints to store like parameters and extra variables as like pointers and things as you're moving them over. So that's just a constant amount of extra things. But the bottleneck is in case 2, you're doubling the size of your array, and so you're making, if your old array was size n, you're making 2n of space plus some helper pointers and integers and things like that. So that's 2n plus some constant c, which is always pretty small. It's like 4 or 5 maybe, or even less. And that is going to, like, as n gets large, the 2n is taken priority, right? So if like you had 1 million things, you have to now allocate 2 million and 5 maybe things. So it's the 2n that's the big deal. And we call that linear space. It's like y equals 2n plus 5. As that graph grows, as n gets larger, you have to do more work. That's a linear amount of more work, right? It's the graph of a line, and that's space complexity. So it's not always the case that they happen to be like kind of the same, like constant, linear. But that is not necessarily true for space and time complexity. Sometimes you have usually it's a trade-off. Usually it's like, to have really good time complexity, sometimes you have to allocate some more space. Or to have a really good space complexity, you have to spend more time optimizing, and so it takes longer to run. So usually there's a trade-off. This is one of the cool cases where it's kind of, they went hand in hand, but that's not always the case. Okay, so that's space complexity and time complexity. And again, we're going to study these things in detail soon, but I just want to get you used to hearing these words before we define them for real. All right, and with that, I want to completely change gears. I want to talk about a topic that will be the bulk of the rest of the lecture. It will be called separate compilation and makefiles. And this is going to help us compile things faster, because one day you're going to have a really big project and you want to like compile it as fast and efficiently as possible. And we want to know how to do that. So let's learn how. So pretend you've got a project with like 1 million files, and I'm only going to draw an example with 3 files, but in the back of your mind, please imagine that it was 1 million instead of just 3. So I've got x.cpp and y.cpp and z.cpp, because like one day, like a large software project that you might work on might have like tens of thousands of files, and that's seriously true. So here's a 3-file example to prove the point. But all right, if you change one file, let's say you keep x, y, and z, you keep y and z the same, but you've changed x.cpp after you compiled the last time. So you change like one line x.cpp. The only way we know how to compile right now, or the way that I've taught you in this class so far, is you give them all to G++, and it brings them all together again into your final output file. And if you don't say -o, it calls it a.out for fun. So that's a horrible reality, right? We give like the old files that were just fine. We compiled with those old things before, but like there's no remembering that right now, which is unfortunate. X.cpp does have to be recompiled because that's the thing that's changed, but Y and Z, they have to come along for the ride as we give them to G++. So that's no fun. That's very inefficient. The answer is no. So to get to the right answer, I want to teach you more about compiling and linking. All right, so yeah, the answer is of course no to this question, but let's review what it means to compile something, what it means to link something, so that we can all be on the same page, and then the solution makes more sense. Okay, so yeah, compiling and linking. The job of a compiler is to translate a single program into either machine code or object code. It's the same, those are synonyms. So like, just like your single file, your x.cpp, your y.cpp, your z.cpp, they're all being sent to the compiler separately when you use G++. G++ does muddy the waters a little bit because it's both the compiler and the linker, sadly, but that is beside the point right now. So that's what's happening. We're giving all of those files individually, secretly to G++, and it's compiling them into machine code or object code. I'll say object code for the rest of this example. And so that creates like ones and zeros, the binary form that the processor can understand for that one program, for all of like the functions and methods in x.cpp. And so there's like a little intermediate file called x.o for object code. And this happens for every program you give to G++. So we also gave y.cpp and z.cpp. So G++ under the hood is making y.o. The compiler part of G++ is making y.o, z.o. And then there's other object code just kind of laying around. Like if you want to use cout and cin, like iostream has been pre-compiled for us. And it's just being linked together with all that other stuff. So the job of a linker is to combine a bunch of programs together so that we can use all of their things. We can keep on using all of their things. And so unfortunately, G++ also runs the linker for us, but secretly there is a program on our in the terminal that is the linker that G++ uses, and it's called LD. All right, so G++ just kind of uses that for us. Unfortunately, we don't see it when we do this, but I promise it's there. It's bringing things in one at a time, making object code for each individual file, and then linking everything that we gave G++ as well as any library code that we're using. And after all that's done, compilation first, linking second, then we finally have an executable file that we can run on our terminal. That's our a.out that we can run with the /, unless we call it something else. Okay, so that's compilation and linking in a nutshell. And now I can show you what we can do. So there is secretly a way to get at these intermediate.o files. And the way you do it is to call G++ a few different times with this -c command. All right. So the -c tells G++ to just compile only, C for compile only. And that will, you just say it like this, you don't have to do -o because it just like by default, you give it one file, it'll turn your output into that file name with a .o at the end. All right, and that's the machine code or object code for that one source code file. All right, and that's nice because the goal is to keep y.o and z.o the same. All right, we don't have to change them. We don't have to recompile those. We just have to relink with a new version of x.o. And linking is really fast. The bottleneck is definitely the compilation process. So that's great. This is going to save us time, especially when we have millions of files. Okay, so I want to use the counter class as an example. Let's steal that from last time. Or 2 times ago, excuse me. So there's my counter.cpp file from lecture 2. Let me copy that into here. And then I want to, I'd like to split it up. I'd like to split this counter example up into like counter code, a library, like a header file for the counter code, a implementation file for like all of the counter library implementation stuff, and then just like a file with just the main function that uses our library. Okay, so that's what I'd like to do. So let's split this program up and we will go from there. So let me confirm that's what I want to do. Yeah, that looks good to me. So let's say that this first bit is like counter.h. So all this stuff can be counter.h. Let's get it started at least, counter.h. And I will for sure steal all of this. Don't forget about your header file guards. Boop, all those guys. There's counter.h. It has no clue what a vector is right now, so we're going to have to include, I think iostream as well as vector, because we're also saying friend, or no, the output operator is not a friend, so that's fine. I guess I didn't have to do iostream here, but we'll figure this out together. So this needs to be standard : vector for a reason I said once upon a time. You can never use namespace standard in a header file. That is a bad decision because the second somebody includes a header file, that means that all of your code is being copied and pasted into that file. So we do not want to make a choice for the user of our header file. We would like to just like be as generic as possible. So we'll say standard : vector in this file, and that should be okay. Let's see here. I think I do want iostream there because as we implement stuff, there's one thing I also want to like make part of the library, and that is something that wasn't declared in counter because it's not part of the counter class, but this output operator. That's just a function, but it can be declared just so that we know it exists in this file. So that's perfect. That can be part of our library, and that is for sure iostream. So I guess I could have kept it like this. And it's going to be standard : o stream, standard : o stream. And then it knows about counters, of course, because it's the same file. So that's the header file. Let's next do the CPP file. I guess we already have it. So what we'll do for the CPP file is we'll include our library, include counter.h, and then it knows about like what it means to be a counter, because that's defined there. And then you can say using namespace standard all day long in an implementation file. That's fine. So all those things about counters and the operator, that's part of the library too, go there. And then I'll make one last file. Let me save this. One last file with the main function. And I like to call that, I guess, main.cpp. So I'll put that there. And main.cpp, we can include counter.h. And we can use namespace standard all we want. And it's happy. And we get cout and stuff for free because iostream is included with counter.h. So that's fine. I guess we don't have to do anything other than include this. So that works. And so now I've got 3 files that kind of work together that make up this library and me using it. Okay. Oops. So there's the header file. There's the CPP file that implements everything in the header file. And yeah, and then here's the main file that includes our library and like actually does something with a main function. So here is me compiling and running all of that. So the way that we knew how to do it before was g++ main.cpp counter.cpp, and then you can call it, I'll call it main perhaps. Like that was a final program. But the idea was if I change one line of main.cpp, like I have to recompile also everything in counter.cpp, even though it didn't change. So the goal is to have these intermediate steps and go through these .o files. So let me show you the -c now. All right, so let me remove this main compiled thing. I want to go to .o files individually. So what I'll say is I'll say g++ -c for just counter.cpp. And I hit enter, and it's going to make a counter.o file for me. And then I want to make it also for just main.cpp. Just make main.o, please. So g++ -c main.cpp, and that gives me main.o. And so I've got both of these pre-compiled things. They're not runnable yet because they need to be linked together, but like that's what you'll do for each of your million files. And to finally do the last process of linking them all, to hand off everything to the linker, you can also still say g++ and it will figure out what you want. But here's the secret. What you do is you give g++ all of your .o files, and then you can say -o, like what do you want the final thing to be called? All right, so linking is really fast, compilation was slow. And so if you can avoid compiling too many things, like you just have y.o and z.o and all your other million files laying around as .o files, you can just recompile x.o if x changes, and then you can just relink the new x.o with all the old .o files, and that's lightning fast. Compilation was what would take you like hours for 10,000 files or something. So that's great. Let me show you that. So if I say g++, give it all the .o files, counter.o, main.o, and then call the final thing main, it's happy, and it runs. And that's really nice. And so if I change a line of one of these files, then I'm set. Then I can really easily get to what I want, because if I add another line here, let's print out C3 again, then it's just main.o that needs to be recompiled. So give it the new, like recompile just main.cpp, keep the old, this is the new main.o, the old counter.o, and now I relink. And now I'm going to get that thing printed out again. Beautiful. So that was much faster. Imagine a million files. That was the blink of an eye. That was great. And so that is our goal. All right. So if you had a million files, though, it would be tedious. It would be very tedious to say g++ -c for each of your million files, and then g++ to link them all. And so there's one last thing I want to show you, and that's makefiles. So a makefile is a special kind of programming language. It's a file that you give recipes for how to build your project. And you just write everything once, and then you can keep reusing it. And it will recompile all your stuff and relink it in the most efficient way possible. All right, so that's what a makefile is for. It's a special little language. It's not C++. It's there's a terminal command called make that goes and looks for a file that is a make file. And what a make file is it's just legitimately a file in your current directory called makefile with a capital M. And it looks like this. These are the things that it holds, little recipes for how to build pieces of your programs. Like this is a recipe for how to build main.o using main.cpp. All right. And it's an older language. It looks a little weird. It's not C++. So comments start with number signs like Python does, though this came before Python for sure. And there are some quirks that your editor will just deal with for you. So like if you open this up in Vim or Nano, it'll do it right for you. This is not spaces. This is a legitimate tab. It's a tab character. Your editor should handle that for you if it knows about makefiles. And what you give in a makefile is just a bunch of terminal commands that's saved away for how to build something. So like this is the terminal command, and you can have multiple of them as long as you stay indented. These are a bunch of terminal commands for how to build what you want, for how to build main.o using main.cpp. That's kind of what that means, and I'll teach that to you. Commands. So that was like a rule for main.o. Similarly, a rule for foo.o. All of these are tabs. You tab over to get to all the the algorithm to build your final thing, and you can have many lines there. All right. So yeah, this taken together is called a makefile rule. This is a rule to build foo.o using foo.cpp. And so everything after this colon here on the first line, those are called your requirements. And I'll explain this last one after I circle or with a dashed line that. So these are your requirements. Those are your ingredients. That's what you need to build your final thing. So like if you want to make your final program called prog and it uses main.o and foo.o, you have to say I want those. Those are my ingredients. Those are my requirements. And then once I have them, here's how I use them to build the last thing that I care about. All right. So that's the goal. So yeah, I hope that makes a little bit of sense. Let me teach you what it means to make a makefile rule, and we'll do it for our counter example. So, okay, here is my standard example that I like to give in CSCI 40. Here's how you use a makefile. Here's how you write a makefile rule to build a peanut butter and jelly sandwich. So you got to give it a name. The first thing you write is the name of the thing you want, the name of your rule, the name of your target, you say. This is your goal, your target. So I'll call it PB_J. That's a standard thing. You can't have spaces or anything. It's like a variable name. And then you put a colon and you say all the ingredients or requirements that you need to go and build a peanut butter and jelly with. So what do I need to build a peanut butter and jelly? I need a plate. I need a knife. I need peanut butter. I need jelly for sure. And then I need bread. That's a start at least. All right, and let's say that that's all my ingredients. And once I have those, I can go off and build peanut butter and jelly. And so I give the rule to make peanut butter and jelly from those ingredients by tabbing over on the next line and giving as many lines as I need that completes the recipe that uses these ingredients to build the final target. So how do you build peanut butter and jelly out of those things? You got to open the peanut butter jar, right? That's one line. These would be terminal commands, really. Then this is open the jelly jar. And then you got to take out 2 slices of bread, right? Dot, dot, dot. Eventually, you can write it all out, and then you close the sandwich, and it's ready to be eaten. Okay, so that is how you make a peanut butter and jelly. This is how you make a makefile rule. You say what you want, name of your target, which is usually the name of the file you're trying to build, and then you give all the ingredients, which are other files that you hope to exist. They better exist first for you to do anything. And then you tab over and you give a bunch of terminal commands for how to slowly but surely build the final thing you wanted out of these ingredients. The rule will not run unless you have those ingredients. But one really nice thing about makefiles is that say you really wanted peanut butter and jelly and you asked the makefile to make you peanut butter and jelly, but it noticed that you were missing an ingredient. It noticed that you didn't have peanut butter, for example. It will try to go looking for another rule in the makefile for peanut butter, and if it can find that, it will run it first. So if it doesn't have peanut butter, it will go looking for a rule for peanut butter. And so maybe you write that too. What's a rule for peanut butter? How do you make peanut butter? I can do like peanuts in a blender, or you can have a car and money. I mean, the process is go to the store and buy peanut butter. and ta-da, you have peanut butter. And so it'll go and run every rule that it needs. If it sees that you need an ingredient, you ask the make file to make you peanut butter and jelly, it sees you need an ingredient that you don't have currently, it will go looking for a rule to make that thing, run that rule, and then come back, and now it's ready. That's the magic of make files. So it's going to automate the compilation and linking of your program in the most efficient way possible. I'll show that to you. So that's really nice. And so back to code land, back to actual files and things. Here's kind of the deal for a make file rule. It's like the name of the thing you want, which is a file name. We call that the target. And then you space separate after a colon all the ingredients that you need to make the thing. So those are your requirements. That's the technical term. Requirements. They have to exist. Each of those things, those are file names. These are files that you better have before you run the body of that rule. And that must exist before the body of the rule can be run. Okay, and then the body of the rule after you tab over is just all the terminal command line commands that you need to do in order to make the thing you want, the target, out of the requirements, out of the ingredients. All right, so it's not too bad. Steps needed to make the thing. I hope that makes enough sense. All right, so now back to this example. I hope you can kind of see it, right? To make main.o, I better have something called main.cpp lying around. If so, here's how I use main.cpp to make main.o. Here's the terminal command that turns it into that. And you only need one for this rule, but sometimes you need multiple lines. So there's that one, same for foo.o. And then for the final program that needs both of them, you give both .o files, like I better have those precompiled, and then here's how I link them together to get the final thing I wanted. All right. And the beauty of makefiles is you can say, I want makefile language, please make prog for me. It will go looking for main.o and foo.o. If it doesn't find them, or if they're out of date, like something's changed, it will recompile just the ones it needs and then run the body of the rule you really wanted. That's the beauty. So you write one makefile just once and for all, do it right. You can compile your million program project, your million file project very efficiently and quickly. All right, it'll just always do it right. And so, yeah, let's make a makefile for our counter example. Let's see. So I want to make, oops, oh goodness. So I want to make a new file. Let me, by the way, also remove all of my compiled things. I'll remove all my .o files in main. So now I'm just back to the original stuff. I'm going to make a new file called just makefile with a capital M. And here's how you do it. All right. So you're going to give a bunch of rules. You can have comments in your makefiles, and those start with number signs. So this is a makefile comment. And then you give all your rules. So let's say a rule to make main.o. You say main.o is the name of the rule. That's the target, colon, and what do you need to make main.o? I need main.cpp. And then I hit enter, and my editor automatically tabs over for me. So yours should too, unless maybe you're on Nano. Nano might be weird. I'm really not sure. Learn Vim as fast as possible. So G++, to make main.o out of main.cpp, you say G++ -c on main.cpp. Yeah? So that's the rule to make main.o. Similarly, you can do the same thing for counter.o. We want counter.cpp, that better exist, otherwise we can't do anything. And here's how you use the ingredient to make the target. Okay? And then finally, the final thing we want is main. That's what I want my program to be called. I better have main.o and counter.o ready to go. And here's how I link them together to make main. I say G++, give them both, and then -o main. That's the name of my target. And that becomes my makefile. Does that make sense? And so that's just another file in your current directory. And you can ask the make language to wake up and notice this file and start building things for us. So to run your makefile, here's how you do it. There's a terminal command that looks for the makefile. It's just called make. That's useful. You say make space, the name of the target you care about. Okay? So I can say make main.o. and it runs that rule. Make counter.o, and it runs that rule. And it only runs it if it notices that it's out of date, like something's changed. If I rerun make counter.o, like it's already there, it's happy. Then I got those .o files, I can say make main, it finds them, and then it links them, and I've got something. I can run it. The beauty of make files, also, the very first rule you put is the one that gets run. If you just say make by itself, this will run the first rule. So you usually put the most important one first, like main. But we can do that up here. Like that's the first rule now, so that's the one that runs. If I just say make, it'll try to run the main rule, but it's up to date, nothing's changed. But let's remove all the .o files and the compiled files again, and let me show you the magic. If I just say make, that means it's gonna do make main. If I just say make, it's really gonna do the same thing as make main because that's the first rule now. If I hit enter, I don't have any .o files, but it notices, hey, I need main.o, but I don't have it, but I see a rule for that, so I'll run it. There it goes. And it prints out as it's running. I also need counter.o to make main, but I don't have it, but I see a rule for it, so I'll run it. And then it's like, okay, now I have everything I need. Here, let me run the thing I care about. That's so nice. It does it all for you. Just say make, if that's the first rule. I could have said make main. Either one works. And if you change something, it'll do everything in the most efficient way possible. So if I change main.cpp again, I say that again, then it's main.o that needs to be updated, right? If I just say make main or make again, it will notice that. It will notice that counter is fine. Counter.o hasn't changed. It's looking at file modification times to figure this out. And it's like, all right, I need to remake main.o. Here's the rule for it. There we go. And then it uses the old counter.o because it hasn't changed. It notices. And then it relinks them all. So in the most efficient way possible, make will do what you want. And so that's the beauty of make files, and I hope you see the power here. All right, so that's very useful. It'll save us a lot of time, and you just like write how to compile your program once and for all. You're off to the races. All right. Some fancier things you can do in make files. There's some shorthands, and there's special variable names that start with $signs most of the time. Let me show those to you. All right, so this is like the old version, original makefile. I'll copy that into makefile old, so you can still have it. Oh, sorry. Copy the current makefile into a file called makefile.old, and then I'll re-edit the original one so I can still run it. So some fancy rules in makefiles is the @sign. $@ is shorthand for your target's name. So instead of saying -o main, because main is the name of the target, I could have said -o $@ Yeah, so that would work. And if you need the list of all of your ingredients or requirements, that's $caret. If you just want the first thing that's listed as an ingredient and the others didn't matter, when you're doing what you need to do, $$ gets you your first ingredient. So $caret is shorthand for all of your ingredients. So here is me using all the ingredients. So I could have replaced that with $caret. That will turn into main.o space counter.o. Isn't that cool? That's fun. And similarly, main.cpp, this could be equally $caret or less than, because it's the first and only thing anyway. So it's happy. So I could have done that, $caret, and it's happy. But yeah, either way, either one could have worked. And let's see, that works. And then also variables are useful sometimes. There are, believe it or not, there's multiple competing options for compilers for C++. There's one called G++, and then there's another one called Clang++. I don't know if I have it installed right now, but that's the thing. That's what Macs install. But they rename it to G++ just in case. But there's other C++ compilers, and so it's useful to make a variable to say which one you want and just use that everywhere. So the C++ compiler I want to use is G++, so you can't say C++ and make that a variable name. So we can do the trick where people just put X's to mean a sideways plus, like my C++ compiler is G++. And you don't put any spaces around that equal sign, which is a little odd looking, maybe, but that's this is me defining a variable called CXX, which is supposed to mean C++. But a variable name and make, just like in C++, cannot have a plus sign. And then here's what I want that variable to be. And that, of course, has to have pluses in it. And that's fine. And then to use a variable, you say $, parentheses around the name of the variable. That accesses a variable and translates into the right-hand side of that equality. So instead of saying G++, I can say $, parentheses CXX, which is supposed to mean C++. This is the C++ compiler I'm using. And so very quickly, if you wanted to use the other one, the other competing popular one, you just change this to Clang++ just up top, and everything else remembers. It just uses that variable. Okay, that's kind of neat. And so there's that one. If I remove all of the .auto files and main, and I say make main again, I could also just say make because main's still the first rule. Nothing changes. It's all running the same stuff, but we're just using the shorthands. Okay, there's that. The last thing is people usually like to add a rule called clean, but it doesn't make a file called clean. What it does is it just like removes all of your compiled files and brings your folder back to a blank slate. That's useful. And so I'll make a rule called clean that doesn't take any ingredients. It just runs some terminal commands to clean up. And so what are my compiled files that I'd like to remove? Remove counter.o and main.o. To remove every single .o file, you can say remove star.o and then remove the compiled file called main. And just in case those don't exist, don't let this complain by saying -f. Just like f means force. Just like if these files aren't there, don't worry about it. Don't tell me about it. Okay, so that's the secret. And that's clean. So a clean rule. Clean doesn't make any files, make anything. It just removes all the compiled files. Okay, and so if I run make main, I've got all these .o files and main and things. If I say make clean, it's not going to make something, but it will run that any terminal commands you put up in there, and that will get rid of all my compiled files. And now I'm back to a blank slate, and I can recompile again. Sometimes that's necessary to just for a sanity check if something's going wrong. And so that's useful. That's another useful rule. All right, so that is a fancier version of the makefile, but we've still got the old one. I gave it to you as makefile_old. Okay, so yeah, that's that. That's makefiles in a nutshell. We're going to use that in our next lab. Okay, the final thing I want to talk about is sorting weird things by using a comparison class. This is kind of an old-fashioned thing, but it still comes up, and so I want to talk about it. Let's make a brand new class. Just a silly one that holds on to one integer. I'll call it holder because it's gonna have one member variable. It's gonna hold on to an int or something, and I want to sort like a vector of holders. Let me show you what I mean by that. Okay. Sorting classes. So maybe I should have said sorting objects, but that's fine. So I eventually want to use vectors here, and I want to use the algorithm library sort function, algorithm. There we go. And yeah, so here's a silly class called holder. And the what it's going to have is, it's just a dumb example, but it's useful. It's going to hold on to an int. All right. So here's a holder. Just to make things easy on myself, here's a constructor that sets that x using an initializer list, of course. And then I'll have a getter that gets that x value. It'll be const, of course. And so this is me being lazy at implementing everything inside of the class. So here is let's make some holder objects now. So holder h1 is a holder object that's holding on to 42. H2 can be a holder object that's holding on to 55. And then H3 can be a holder object that's holding on to 128. All right. And let's make a vector of holders. I hope you can see this might be something you'd want to do someday with a class that you make that holds numbers, maybe. So vector v is, let's have it hold h2, h3, and h1. So it's kind of out of order, right? 55, then 128, then 42, but they're inside of everything. They're inside of the holder. And if we wanted to sort it, I want to say like sort v.begin, v.end. I'm going to get a compiler error because this is sorting classes.cpp. This is going to be a disgusting compiler error because by default, what C++ will do is, this is sometimes the most useless error message, but it keeps saying less than. Less than, less than, less than, and that's kind of the secret here. What's going on? No match for operator less than for two holders, because that's what it's secretly trying to do. What the sort function does, boop, in algorithm, the default way it tries to sort things is, where is that? The default way to sort things is it's going to try to see like which thing comes before the next thing by using a less than operation. I promise it's here somewhere. Yeah, so here, the elements are compared using operator less than for the first version of this kind of sort operator, okay? For this sort function. So that's what it's going to do. It's going to go looking for an operator less than on holders. Take two holders, give me whether or not one is less than the other. Because that's all you need to sort, like that. That'll tell you which thing comes before the next thing, and that's how the sort function in the algorithm library is implemented. All right, so that's option one. Option one, if you want to sort stuff, you make an operator less than for holders, and then this would totally work. It would go looking for that. All right, so let's do that first, because we know what that means now. So, all right, I want to make operator less than on two holders. I'll take them by constant reference because I'm a good C++ programmer. I'm not going to copy anything. I just want to use their memory for a second, and I can return a bool, right? It's going to check if A is less than B, and I need to return true if that's true. So let's say that holders are compared by using the things inside of them. So I'll use a getter because this is not part of the class. So I'll just return whether or not A's x value is less than B's x value. Do you see how that's telling me whether or not, A is less than B for my definition of less than? It's just comparing the x's inside of the holder. Yeah, and that should be all I need. Is that happy? Should be. And then let me show you it being printed out or something. So like for every holder, I'll take it as constant reference again, called H and V, look at each one of those and just like see out that holder's X value. Space separate. This will work. Unless I made a mistake. But morally, this should work. Yeah. So it wasn't in that order, right? Because I put the 55 first. But it changed and it sorted and it was fine. Because the sort function would just go looking for like, how do I know when one holder is less than another? And I told you how. All right. So that works. That's option one. Option two, there's a couple different ways to use the sort function. There's another way to call it. This was the first default way. The other way is going to use whatever you pass as a third argument. If you give a third argument, like, all right, start and end memory locations, and then also something that lets you compare. You can also, you can pass a function here. You can pass a function here, or you could pass a class that is called a comparison class. So that's where I'm going. All right. So yeah, sort by default uses operator less than. That's your first option. Option two is you make a function that's not called operator less than that compares potentially in a different way. All right. It's just like this is a function that kind of functions like operator less than, but maybe you wanted like to sort in a different way, like with bigger things coming first. So you make a different function called something different. All right. And so yeah, let's make a comparison function. And the idea of a comparison function, including operator less than, is just you're passing it to sort either implicitly or explicitly. And it's supposed to take two things that you want to sort and give back true whenever the first thing should come before the second thing. So like that's what operator less than was doing. It's returning true when A should come before B, so A is less than B. But you could totally make another function, call it like holder compare, and return true when A's x is bigger than B's x. This means that I want to prefer, right? I'm supposed to return true when A should come before B, so I want to prefer bigger x values. Does that kind of make sense? That is another way to call it. All right, so that's option one. Let me comment that out. Option two is you pass your own function. It's not like the default name anymore. Option two, make a comparison function. Because sort can accept a third argument, call it holder compare. Pass the name of the function. It will call it for you every time it's trying to see which one needs to come before another one. So it'll be like, all right, every time it sees like, should A come before B? It's asking that question inside of sort a bunch of times. We're returning true when A's x value is bigger than B's x value. So it's going to prefer bigger x's first. Okay, that's the opposite of less than. This is really a greater than function. So that's another way to do it. And so now if I recompile, rerun, now I get bigger things. So this is me saying, use this thing, please. I'm passing a function to a function, which is kind of cool. Maybe you've never seen that before. It's just going to use that to see which things come first. All right. There's one last weird option, and that's kind of the oldest option. It's called a comparison class. All right. Another word for that is a functor. It's a weird name. It is a class that has the operator parentheses operation overloaded. So it's like you can call your object like a function. That's what it means to have this operator parenthesis overloaded. It's weird looking. And again, it's supposed to take two holders and return true when the first should come before the second. So this is kind of more clunky, but this used to be like the old way to do it. So let me show you that last secret way, but it's not secret anymore. So option 3, if you want to sort a vector of things, is you make a comparison class. Okay. And here's how you make a comparison class. Again, I'll be lazy and implement it all inside the class, but it's got to be a class, so it's holder. I'll call it something normal sounding, comparison class, and then it will take, it'll just have one method in it. It's an operator parenthesis that returns a bool. All right, it's weird looking, and again, it takes two holders. So it looks like this again. Takes two holders or whatever thing you're trying to pass to sort, and then it's again trying to return whether or not true when the first argument, which we're calling A, should come before the second argument, which we're calling B. And here I can ask it to prefer smaller things again. But this is a little clunky looking, but I've overloaded the parenthesis, like the function call operator of a class. So it's like an object and also a function I can call at the same time. That's why we call it a functor. That's another name for it. So it's really weird. I can make an object of type holder comparison class right now. Watch what I can do to it. Boop. I can make a holder comparison class object called HC maybe, because is legitimately just a class, right? Here it is. And what can I do to it? What can I do with it? I can call it like a function because I've overloaded that operator. That's so weird. So I can say HC, give it two holders. Isn't that disgusting? That's so weird. You can do that though. That's what it's allowing. You've overloaded the function call operator for your object. You can treat it like a function. Isn't that so cool and weird? So H1 is 42, H2 is 55. So this should be true. This should totally be true, weirdly enough. All right, so there's that. So it should print out true. And it's not actually sorted anything yet. 1 for true. And then you could pass this thing, anything, just like for this holder compare, it's something that it can call, the sort function can call. For all intents and purposes, this HC can be called. And so C++ is happy if I also pass that to sort. That's me using the comparison class. There. That is weird. That is weird, but it will work. Isn't that crazy? And so here it is sorted. And the documentation is kind of helpful here. It's like, all right, this thing called comp is some sort of binary function. So it takes two things, a function or anything like a function, right? Something that has that operator overloaded. That takes two things, and the return type is something that it should be a bool eventually. We're hard coding it to bool. The value return indicates whether the element passed as first argument is considered to go before the second in the specific strict weak order. So it's got some fancy words that you can look up if you'd like, but that's the idea. This can either be a function object, which is kind of what we just made, or a function pointer, which is when you give the name of an actual function. So don't worry too much about that, but these are all words that you can look up. I've shown you all the different ways you can use it though, all right? In a way that you can understand, I hope. So that's kind of neat. There's actually one secret fourth option if you've heard about lambdas in C++. There's a way to make a function without needing to give it a name. So like if I only needed operator less than for one call to sort, it was kind of useless making an operator less than way up here, kind of out of the way, like adding 3 lines of code for no real reason. One thing you can do, option 4, you can make a function that doesn't have a name in line inside of main. So it's a cool newer thing in C++, but it's been around for a while. And so here's how you could do that. You say sort, and again you say the range, sort from begin to end, and then you can make a what's called an anonymous function right here. So instead of saying the name of a function, you can give the implementation of a function. And so here's the silly syntax. It's like empty brackets there, square brackets, and then you say the arguments, const holder reference A, const holder reference B, and then you give the body, return whether or not A's X value is less than B's X value. And you can just do it in one line. This is a function inside of main. This is called an anonymous function. Doesn't even need a name. Just like, hey, C++, use this one. It's this function that takes these arguments and does this. Isn't that cool? Let me zoom out so you can see it all at once. Like that's using what's called an anonymous function. And that will also work. But that one's a little fancy. I'd be happy to talk more about it, but comparison classes is the last one I really cared about teaching you. All right, so I hope that makes sense. If you want to sort something, you got to tell C++ how to sort it, like which things come before other things. So you could either use the default operator less than, you could make a function that does something maybe other than less than to prefer values that should come first. And you could also make a class that has a function call operator overloaded so that you can pass an object to sort, but C++ can use it like a function so it's happy and fine. Isn't that so weird? So yeah, that's as much I want to melt your brain tonight. And I think that's all that I wanted to say. That's the end of these slides now. So yeah, please yell at me, ask me lots of questions if you have any. Come to office hours, go to the tutorial center. But that, my friends, is the end of these slides on OOP and ADTs. You now know how to make vectors as well, and then make makefiles to very efficiently compile your vector lab that I'm about to assign to you. So yeah, go look at the next lab introduction video. That should be somewhere near this one. And I will see you in the next one.